base of a solid S in the region bounded by the graph. Their cross sections are still semicircles. Looks like we're going from left to right. So I'm going from A to B, so I got to use that as, I'm going to pop this out, move this over here. Away zoom window. Okay. So we have from A to B, not that one, not that. So it's restricted between A and B. We're talking about perpendicular to the x-axis. So from the most left one, it could be A, to the most right one, it could be B. So that's our limits of integration. That's check number one. Get rid of C and D. They don't go from the same limits of integration. Now, as we create the semicircle, we're taking G minus F. This is the area between curves idea. So in order to have a radius, in order to have the radius pi r squared divided by 2 for the semicircle, in order to have that radius happen, we got to go from G to F. So I'm looking for G goes first, F goes second. Oh, they both have that. They both have squared. Why would this be over 8? Oh, okay. So from G to F is a diameter, but when we want radius, we got to cut that in half. So it's really diameter divided by 2, then you square it, then you cut it in half. So R, the radius of the semicircle, is the diameter cut in half. So D squared, that's, I'm pointing at my screen, but I'll use my mouse as well. G minus F, that's D. Square it, divided by 2, square it, divide that by 2, so 8. I don't know if all of my fingers were in the frame. Check. Okay. The base of a solid S in the region bound by the ellipse is 4x squared plus 9. You know, if 4 and 9 were the same, you'd have a circle with radius 6. I forget, what does the 6 represent in an ellipse? It's like the, what do they call it? From focus to focus, the distance between them, or distance from the circle to the focus of the, anyway. Cross sections perpendicular to the y-axis are isosceles right triangles with a hypotenuse lying on the base. So draw it time, and let's minimize this. Again, this is just behind the scenes. Okay, so we have our ellipse. We've got like this. Ooh, what's the height? Isosceles, isosceles right triangles. Okay, so there's a right angle right here. And there's a right angle. You know, they all actually line, if like as a projection from the top, they all line up with the y-axis. So all of these are right angles. You just gotta like trust me that that's what I'm talking about. They're all right angles. So it's like this, oh gosh, concrete mixes or like excavation yards, whatever. Then when they're dumping things, if they dump it ever in a line, you're gonna get like this ridge, you know, in the middle, you know, mountain range, but the smoothest, most, you know, symmetrical mountain range ever that spreads out evenly on either side of it. I drew this whole thing, and you can't even see it. It's behind the scenes. Okay, so the distance from here out to the edge, that distance could be described as in x equals, if I can take the ellipse formula, 4x squared plus 9y squared equals 36, and I subtract 9y squared divided by 4, so this is not the right way to write it. I'll just kind of like read it. So it'll be 36 minus 9y squared over 4. That's going from, squared. So square root. So that's going from x out. That's the first line of the radius. If I want the whole base, what is the formula for an isosceles right triangle? I think it's 1, 1, root 2. Or if I make it line up with what's going on there, root 2, 1, 1. Okay, no, leave it. So this line out to here will be the same as the line popping up. So I have like a marker. Over here. Happen again. Flimsy technology. This line is the same as the height of the triangle. That's the genius part. So if I find this half, just by using base times height, ooh, this is the base and the height. Yes. So base times height, that gets rid of the square root. Oh my gosh. Oh, so much more nice calculations here. Okay, so if I find base times height and I get this section over here, I can just double it because I have, symmetric. So I'm gonna go, volume is still base times height, but on the left side, this cross section is an isosceles right triangle. Trust me, it is. So it's gonna be base times height, and then h depends on where we are with the y value. So our y value is going to go from -2 to +2, -2 to +2. So this is our limits of integration. Write it out, limits from -2 to +2. Call this base of y times dy. What the other one had pi because we're talking about semicircles. So this really, wait, it's a triangle. Almost missed it. So triangle, so got to divide by 2. Right? Base times height, divide by 2. Can I get away with something here? At some point, I'm going to multiply it back by 2. So I might as well, because it's 2 of them. So I might as well do the doubling inside the integral because there's the other triangle on the other side. So this base and this base, I'm just going to cut that 2 out because we're doubling it. So then I am going to use just this. The volume is the integral from -2 to 2 of 36 minus 9y squared over 4 dy. Again, I don't need the square root because I'm squaring it. I'm squaring it because base and height of that right half are the same, doubling it. So base times height divided by 2, but I'm doubling it, so just base times height. So then, wow, that's so nice. Okay, so then we're going to go ahead and do this integral. We want an exact answer. Are we typing it? Yeah, we are. Okay, so, I can further do this. I can go the integral from -2 to 2 of 36 over 4 dy minus the integral of 9 over 4 y squared from -2 to 2 dy. Does that do anything? Okay, the first part does. So for the first part, this becomes 39, 9y from -2 to 2. Yep. Minus, bring this out front, 9/4 y to the third times 1/3 from -2 to 2. So let's rewrite this a little more cleanly. I'm just going to jump into that one right now. 18 minus -18 minus 9/12. 9/12 is 3/4 y to the third from -2 to 2. So 36 minus 3/4 of 2 cubed minus -2 cubed. 8 minus -8. 16. 36 minus 3 times 16 over 4. 48 over 12. 24. I'm saying the answer is 24. Leveled up to familiar. Okay. I'd make it a shorter video. Maybe I'll just like crop it and just be like, here's question 2, here's question 3. So you're probably watching question 4. Oh, wait. So you're probably watching question 4. The base of a solid S is the region bounded by the circle x squared plus y squared equals 16, right? So those coefficients 1 and 1 on x squared, y squared, they're equal. That makes a circle. Cross sections perpendicular to the x-axis are equilateral triangles. Yeah. So here's a circle. Cross sections are equilateral triangles. Okay, so they all pop. All of these lines are the same. It's the exact same thing as the other problem. I'm going to post like 3-second snapshots of my work. So whatever's happening now, I'm going to go like 5 steps forward, put it on here, freeze frame. 5 steps forward, freeze frame. 5 steps, freeze frame. I'm just going to put that in the video because you don't need to see my whole thought process here. You can go back and watch what I did with the other one. Same idea, just sideways. Okay. Check it. Oh, check that out. Like it actually liked this crap. I didn't need to go even further. Oh, just okay. All right. Well, maybe that was an interesting like few minutes for you, or seconds, however long you like. Here's all my work. Go away, backstory. Here's all my work. Done right. I almost had like a brain fart right here where I thought, oh no, I can't have 128 minus 128. And then I realized it was divided by 3. So then I was like, that's fine. But that will happen. You'd be like, oh, I got it twice and one's minus up. If that doesn't happen to you, are you even trying? Okay. So upon division by 3, I thought I should reduce the fraction. I should take it and figure out, and go that extra step algebra-wise. You know what? You can't see my face. You have to see my face. It didn't even matter. I mean, I had to type the right answer, and I did. I didn't reduce it. I didn't combine like terms right here and make this expression simpler because I didn't have to. All right, that's my video. Spent a lot of time doing this. Hope you enjoy. Thanks for watching. Behind the scenes. I don't know why YouTubers always say this. Comment, like, subscribe, as if, like, I don't know, you already haven't. I don't know. Have a cup of coffee.